Hi everybody. In this video lecture, we're going to be looking at portions of chapter 5. So I say portions because we're not going to be covering everything. The things that we are not covering are specified in the study guide. However, to make your life a little bit easier, I have uploaded a set of notes for section 5.1 and 5.2, where I have explicitly crossed out everything that is not going to be covered. So we are only looking at discrete joint distribution. So if you see anything which has double integration, that is continuous, and we are not going to cover it at this stage. So let's get into it. All along, we've been looking at random variables, but we only focused on the one. For example, age. If we wanted to find out the characteristics of the age of a certain population, we maybe found the variance or we found the mean, etc. In this section, we're not just focusing on one variable. We could be interested in the relationship between age and, for example, say blood pressure. Is there a connection between a person's age and their blood pressure? In the past, we could have also just focused on hours. It could be hours of anything. But in this section, we're not just going to look at one variable, we're going to look at two. So for example, hours of exercise and body fat. And lastly, instead of just looking at one variable such as average income, we could be interested in seeing if there's a relationship between average income and years of education. So in a nutshell, the objective of this section is to examine and evaluate possible relationships between two variables, so specifically two at this stage. On page 101, you have this definition. So it's the one that you know from section 3.2. This one gives you the definition of a probability mass function. So if you remember, the probability mass function of a random variable x, that's just this, is just the probability that x is equal to that specific value, which is equal to x. So now if we bring in 5.1 now, page 223, you have this definition. You have what's called a joint probability mass function. So it's still a probability mass, but now you're considering two variables. So instead of just writing px, now you have px and y. So x is the one variable, y is the other variable. And then remember I said we're only focusing on the discrete case. So that means you have x is equal to some value and x is equal to y. So it's very important that you notice that it is an and. So it's the same as an intersection. The first case that you've been looking at all along when you focused on one random variable is called the univariate case. So there's only one variable. When we look at two variables, we call it the bivariate case. And if we're looking at more than two, so it could be 3 or 4 or whatever number, then we call it the multivariate case. But we're only focusing on the univariate and the bivariate for this module. So first of all, I just want to show you side by side how this compares with what you've done beforehand. So let's look at the univariate case. This you're familiar with. Suppose y is the amount of memory in a purchased flash stick. You could have written the probability mass function in the form of a table just like this. So for example, here where you have y is equal to 1, that this probability here, py, is a probability that y is equal to 1. And then you should be able to understand the rest of the table. Now in the bivariate case, this is an example here. X is the cost of the man's dinner in some scenario, and Y is the cost of a woman's dinner. And what they've done here, they've listed all the possible values for the cost of dinner. So it could be 20 bucks, 25, or 30. And it's similar for Y as well. And then what you have inside the table is just like a contingency table. You have the probability of observing this value and that value. So for example, the probability of the cost of a man's dinner, which is X, being equal to 25, and the cost of a woman's dinner, which is Y, being equal to 25 as well, is 0.10. This table is called a joint probability table. Just in the same way as all these values sum to 1, you're going to find that all the values in the table also sum to 1. Now, graphically, in the univariate case, this is what your relative frequency graph would look like. So you'd have all these different bars for the different lengths. You'd have the relative frequency in the vertical axis. And then in the univariate continuous case, specifically the normal, then here you're going to have this continuous curve, okay, which you've seen before. Now, in the bivariate case, here you're going to have all these bars. So it's three-dimensional. On one axis, you have the one variable. On the other axis, you have the other variable. And on the vertical axis, which is the height of each bar, is going to be the frequency or the relative frequency for those two values. In the continuous case, now you end up with this smooth looking bell-shaped thing. So it just looks three-dimensional as opposed to this case. So this is how it looks, and it's the same thing where you have one variable, in this case y, on this bottom axis, and then you have the variable x also. And then the heights, the area, you actually still find the area under this curve to find probabilities, but like I said, we're not looking at continuous bivariate distributions. You're going to do that in second year, and you will be finding areas under this three-dimensional space eventually. So now we just want to have a brief look at how you read the table, just in case you're not quite comfortable with it, just to make sure we're on the same page. So if you have this joint probability table, you'll always list the possible values of x on the one axis and y on the other. So it doesn't matter which way around you do it, you'll still be able to read it the same way. And then inside, as I said earlier, you're going to read the probabilities. So this is the probability where x is equal to whatever is in the horizontal axis and y equal to whatever is in the vertical axis. So if I wanted the probability that x is equal to x1 and y is equal to y1, then I'd look in this cell of the table. Similarly, if I wanted the probability that x is equal to x2 and y is equal to y2, I'd just go down and across at the relevant values, and I'd get the probability in this cell. So the other ones follow in a similar way. So we can look at a quick example. It shouldn't take too long because it is pretty straightforward so far. So in this case, if I'm interested in finding the probability that x is equal to 1 and y is equal to 1, in other words, using that notation, you can rewrite it as this P11. So it means exactly the same thing. So like I said, you look for 1 on the x-axis and 1 on the y-axis. Then you just go down and across and you end up with 0.2. So that's your final answer. You can try this example on your own and just verify that the answer is 0.06. Now, before we get on to the next part of that definition, I want to just highlight some background just to make sure you understand the meaning of some of the notation. So suppose I asked you to find the sum of your x values from x is equal to 0 to x is equal to 2. This you just keep taking what's in there, and then you substitute all the values from 0 to 2. So you take x equal to 0, x equal to 1, x equal to 2, and then you just sum everything. Similarly, let's say you had y cubed. You'll take all the values between 1 and 2, and then you'll just cube them and sum everything. So now you'll see in the textbook they have this thing where you have a double summation. Now, all that this means is that now you're going to consider all the possible values of x and y. So each and every single pair of x and y values, you're going to plug them in there, and then you just do the summation for each one. So the easiest way to make sure that you get all the possible values is to write it in the form of a table. So this is an example here. So I said x runs from 0 to 2, so I've done 0, 1, 2. Y runs from 0 to 3, so I put on the vertical axis. So if I wanted to find all the possibilities, I can just take the 0, 0, or for this cell, the 0, 1. So whatever is across and above, and then I can populate my little table like this. So now what that means for us in this summation is now I need to consider every single x and y value, plug it in there, and then sum it. So for example, this first one, you take x times y. So the first one is 0 times 0, so that's where it comes from. The second one is 0 times 1, so that's where that comes from. So make sure you go through each and every pair. So you go all the way to the end where you have 2 and 1. So in place of x, you put 2. In place of y, you put 1. All the way to the last one, 2 and 3. So you just need to cover the entire table, and then the final answer should be 18. So it really doesn't matter what you have in here. It's always the same procedure. Consider every single possibility of x and y. So in this case, x is 1 and 2, y is 2 and 3. And then you can fill up the table. So here we have 4 different possibilities, and we need to just plug them in here and sum. So here you have 1 plus 2 coming from the first cell. And here you have 1 plus 3, so that's that one. So remember, it's just x plus y. So whatever's in there, you just sum the two things, 2 plus 2 and 2 plus 3. So in a nutshell, despite it looking so complicated, whatever you have in there, so it doesn't matter what function, you always handle it the same way. So suppose you had 2 possibilities of x and y, make sure you just list all of them, and then just substitute the different pairs into your function of 8, and you just keep on summing them. Okay, so remember in this case, our h function would be x times y. So that's why we just kept summing, substituting these values in there, and we just summed across. In the other example, that h function would be x plus y. Okay, so now we can have a look at the second part of the definition on page 233 that I wanted to highlight. It says, let A be any set consisting of pairs x and y. So it's not necessarily always going to be all the pairs, but it's a specific set of x and y values. So some combination of them are relevant and they belong to set A. If you wanted to find the probability that a random pair lies in that set A, then all you do is you take the sum of the probabilities for each combination of x and y in the set A. So let's do an example so you can see what that means. Suppose x and y have the following joint distribution function. What is the probability that x is less than or equal to 1 and y is less than or equal to 0? So we're just going to have a look at it in terms of this definition that they've given us. So they've asked you to find this probability here, and what's inside of the probability is equivalent to your A. So you want to look for each and every single pair of x and y values that belong to the set A. So if you listed all the possibilities, you'd have 0, 0, 0, 1, 0, 2, and so on. In order to check which values are in A, you just go one by one. 0, 0 is in this set. Both of them, 0 is less than or equal to 1 and 0 is less than or equal to 0. If you go to the next value, 1 is bigger than 0. So that observation doesn't belong to the set A. Even the second one as well, 2 doesn't belong, is violating this part, even though x equal to 0 is less than or equal to 1. So this value also doesn't belong to this set. So if you went throughout all the different possibilities, you'd end up crossing out all these options and you're left with these two. So that means our set A only contains 0, 0, and 1, 0. So now to find this probability, remember I said you sum all the probabilities and you take all the x, y pairs that belong to A. So in this case, we have P00 from there, P10 from there. So all you need to do is go to the table and read off P00, which gives you 0.1, and P10, which gives you 0.08. And when you sum it, it's 0.18. Now, I want to show you another way that you could work it out. So it's the same question. Now, another way you can look at it is you're only interested in x values that are less than or equal to 1. So you can actually go to the table, draw a line between 1 and 2, and cross out everything that is not relevant to the question. So in this case, we only want values of x between 0 and 1. So we want everything up here, but we don't want anything below this line. So that's why I've crossed it out. You can do now the same thing for y less than or equal to 0. You only want these values. So where you have y equal to 1, y equals to 2, you can go and cross them out in the table, and then you're left with these two, which is exactly the same as in the previous case, which is P00 and P10, which gives you the answer of 0.18. So it's just another simple way of doing the same question without worrying too much of the maths. So if you're asked to show the working, this is the working that you would show. Well, you can follow the same procedure. In this case, they want the probability that y is less than or equal to 1 and y2 is less than or equal to 2. So I'm going to focus on the first part, and we're going to cross out, or rather block out, what's not relevant to this portion. So you can see here, obviously you have all positive values, so there are no values of y that satisfy this. So you don't even have to waste time looking for the y2 part, because this is an empty set. There are no possibilities of y1 and y2 that satisfy that probability. In the second one, you could get what's y1 less than or equal to 1.5. And you could easily just go and shade it in once again. So 1 is here, 2 is here. So anything less than 1.5 is just 1 or 0. So if you block out the part you don't want, which is 2, you're left with this portion. And if you look at y2, you want the parts where y2 is less than or equal to 2. And in this case, everything is less than or equal to 2. So you're going to sum everything in that block, and you can verify that the final answer is 8/9. In the textbook, there's an example 5.1 that also demonstrates this, which you can have a look at as well. So just with your typical probabilities, there are some properties. So all probabilities are always greater than or equal to 0 for all values of x. And as I told you earlier, if you sum across all the possible values of x and y, so this upside down A just means all, it's shorthand for the word all. If you sum across all the possibilities, so every single x and y in pair in the sample space, you will have the whole table summed to 1. And I told you this earlier, but you can verify this with this table from example 5.1. You can see that both of these conditions hold. Now, when you're given a bivariate table like this, you can actually convert it to the univariate case. So in other words, instead of just focusing on the joint probabilities, you can go back to these simple cases here. This is back to what you know already. And this is what they show you in definition, the definition on page 234. So what this means, really in a nutshell, is if you're interested in the distribution of x alone, then what you need to do is to sum over all the y values. So the way that I remember it is, let's say if you're interested in the distribution of y alone, you sum over the thing that you don't want. So in this case, it's going to be x. So this univariate distribution of y on its own or x on its own is called the marginal probability mass function. So the important part is that marginal. So I'm going to show you what it means in an example, so don't worry too much if this notation is a little bit confusing. So suppose you wanted to find the marginal distribution of x. So in other words, what's the probability that x is equal to x1 regardless of y, x is equal to x2 regardless of y? So in this table, your x1 runs across here. And I said we're ignoring whatever y is. So what we could do is just sum across everywhere where you have x equal to x1. So according to the definition, the probability that x is equal to x1 is just the sum across this row. And similarly, the probability that x is equal to x2 is just a sum across the bottom row. So what you're doing is you're ignoring the impact of y. It doesn't matter what y is. You just want to find what's the probability that x is equal to a specific value. So let's say I have y. If you want to populate this table here, so that's your marginal probability mass function of y. You follow a similar procedure. So you want to know what's the probability that y is equal to y1 regardless of x. So you're going to sum over all the possibilities. So in that case, it gives you probability of y1 is the sum of those two values. So y1 remains the same, and you just sum over all the x values, just like what they say here. Similarly here, you also sum over the different x values, just like in the definition, if you want to get the probability of y on its own. So whatever you have here, you just put it in the corresponding space, the question mark color. So let's look at an example. The marginal PMF. It becomes a question that's exactly like what you would have done in chapter 3. So in this example, we've been asked to find the marginal distribution of x and y. And I'm just going to start off with x and we'll look at y shortly. So if you wanted to find what's the probability that x is equal to 0, as I said, you just sum across all the possible values where x is equal to 0, regardless of what y is. So that amounts to summing across the top row. X can also take on the value of 1 and 2, so you also need to compute the sums across these rows to get those relevant probabilities. So this is how you do it, as I demonstrated in the previous slide. You completely ignore what y is, and you only sum across the values of x that you're interested in. So if it's x equal to 2, this one, and this one have x equal to 2. And you ignore y to get 0.5. So suppose you wanted to find the probability that x is less than or equal to 1. You're back to the univariate case. You're going to treat it exactly like you would have done before. So x takes on the values of 0, 1, and 2. So that means the only values that are less than or equal to 1 are 0 and 1. So you're just going to sum the probability that x is equal to 0 and the probability that x is equal to 1, and you should get 0.5. Or if you do it that way where you block out things, what you would have done now, you're not interested in the parts where x is not less than or equal to 1. So in other words, this x equal to is not relevant, so you can block that out. But remember, the marginal distribution doesn't care what y is. You're only concerned about what x is. So if you've blocked out this part, then you'd sum everything that is left, because you're ignoring whatever y is when you're looking at a marginal distribution. Suppose you wanted to find the probability that y is greater than or equal to 2. So I said we'd find the marginal, so now we're interested in these ones. So you sum down each column, and then you'll get the relevant probabilities for y equal to 0, 1, and 2. Regardless of x, once again. And this is a valid probability mass function, so it does sum to 1. Or even here as well, it was also valid, so it should also sum to 1 if you've done it correctly. So the only value of y that is greater than or equal to 2 is y equal to 2. So you go ahead and just copy that probability directly. And if you wanted to use the method where you just block out the irrelevant parts, you are only interested where y is greater than or equal to 2. So the 0 and 1 are irrelevant. You're only left with this. But remember we said for the marginal, it doesn't matter what x is, so you're going to sum over all the possibilities and you will get the same answer. Now we're going to have a look at what does independence look like in this case. So it just follows straight from what you've done before on page 86. This is what we had. This was chapter 2. If A and B are independent, then this would be the case. Now, if x and y are independent, this is now chapter 5, then you'll find that your pxy is equal to the probability of x, that's the marginal probability, and the product of times the marginal probability of y. Okay, and this has to happen for every single pair of x and y values. So that's for every pair. So if I give you a table and even one pair doesn't satisfy this relationship, then immediately you say they are dependent. And we're only looking at discrete distributions, so don't worry about the continuous one. So let's look at just a quick example. This case, you're throwing a dice, two actually, and you're recording the figure. So y1 is whatever's on the first dice, and y2 is whatever's on the second one, die. Yeah, so then the probability of observing a 1 and a 1 is 1 over 36, a 1 and a 2 is 1 over 36, and you can see the whole table is the exact same thing. Now remember, if you sum across the rows, you get the marginal distribution of y2. If you sum across the columns, you get the marginal distribution of y1. So in this example, it is very clear to see that these two dice are independent, because for every single combination, y1, y2, you have 1 over 36. And then if you take the marginal distribution, you have 1 over 6 times 1 over 6 in every single case, which is just 1 over 36. So therefore, y1 and y2 are independent. Let's have a look at another example. In this question, are x and y independent? So we're applying this. We need to check that every single pair, when you put this probability, is the same as the product of their marginals. So we can go straight to the answer. Suppose we focused on the first block. So P00, you get 0.10. So 00 is there. Now, what if you wanted to find Px0? You just sum across the row. So you have 0.1 plus 0.04 plus 0.02, which gives you 0.16. And if you look for P of y equal to 0, then you go to the 0 column and you sum, and you have 0.1 times plus 0.08 plus 0.06, and that gives you 0.24. Remember, according to this definition, this 0.10 should be equal to the product of that. And in this case, it's 0.0384. But this is obviously not equal to 0.10. So therefore, we say they are not independent. So the very moment you find one pair which do not satisfy this relationship, you can stop there and say that they are dependent, because it's important that every single pair satisfies this for them to be independent. So this leads us to the first exercise that I'd like you to do. Exercise 2 on page 242 of the textbook. I'm going to stop here, and then we're going to go to part 2 of this section.